Thank you very much for the kind introduction and for the invitation to this wonderful conference. So yes, as it was introduced, I will be talking a little bit about work that was done in Dan Rugar's lab at IBM while I was a postdoc. This was a collaboration from the great guys at IBM Almaden, Dan Rugar, John Mayman, actually another member of the conference here, Christian Dagen, which we'll be talking in a couple of days. He now has also his own lab at the ETH. And also, I was involved in this. So I'm going to talk a little bit about the work that we did at IBM by way of introducing this technique for nano MRI imaging. And then I'm going to talk a little bit about what we've been doing in my own lab in Basel, trying to apply this nano MRI technique to semiconductor systems, to semiconductor nanostructures. And maybe, having heard what John was talking about, it might be a system where we could see some of these dynamic nuclear polarization effects, although I have to admit that I need John to explain this to me a little bit better before we go on to that. Okay, so without any further ado, let's move on. So just to give a brief overview of what I'm going to be talking about and the kind of things that happen in my lab, we mostly focus on nanoscale magnetic resonance imaging using force-detected NMR techniques. And we do this using basically applying techniques in micro and nanomechanics, techniques or just using our knowledge of the physics of small spin ensembles and making structures that could be thought of as being in the realm of nanoelectronics and nanomagnetics. So this is sort of a cartoon pictorial introduction to the various things that are happening in my lab and hopefully will be happening in the future. Okay, so I think this is a conference where everybody is familiar with MRI, and I don't really need to talk very much about why it's a good technique. It's a true three-dimensional technique. It's chemically selective. It's non-destructive. So actually, this is a picture of Christian, who's in the audience, and Christian is still alive and well, even though we can see inside his brain. So these are all the wonderful things that MRI is capable of, and one of the problems with it, however, is that it really requires many, many nuclei to make a cubic pixel or voxel. So the kind of goal that was put forward by John Seidels and others and was pursued by Dan Rugar at IBM was to try to do this kind of imaging on the atomic scale and to try to do that using force-detected MRI. So the sort of holy grail would be to try to do atomic imaging of, say, a single molecule or a protein and to position each of these NMR active isotopes in three-dimensional space. So we're still, I'd say, far from this, but we're moving towards that. And actually, to sort of talk about the recent progress in that, I will talk about the work that was done at IBM in 2008 and 2009 in the Rugar group, where we were able to image a single virus particles, in this case, tobacco mosaic particles, with a sub-10 nanometer resolution using this force-detected MRI technique. And I'll later in my talk, I'll explain a little bit how that goes. I won't go into too much of the details, but if you're curious, we can talk about it in the question period. So this is a three-dimensional MRI image. So proton density of a single tobacco mosaic virus particle, which is about it's sort of a cigar-shaped particle with a diameter of 18 nanometers and a length of about 300 nanometers. And you might not believe that this is really, these are really individual tobacco mosaic virus particles. But if I show you an SEM of the same sample, you can see that it's a little bit more plausible to see that we're really making an image of these particles. Now, you might say, okay, well, this image is not really much different than this scanning electron microscopy image, although it really is quite different. This is showing, let's say, hydrogen density as a function of three-dimensional space, and here we just get sort of backscattered electrons in 2D. And actually, when we do such an SEM, we essentially fry all the viruses, and they turn into sort of burned up streaks. And that's not the case with this technique. And also here you can see we have 3D information, so we can choose to look at it in various planes, either the XY plane or the XZ plane. Although you can tell that the resolution at this point was not yet good enough for me to tell you anything about the structure inside this virus. And this could be something for the future. Okay, so how does this kind of technique work? Well, it's quite simple, and it goes back to something that John Seidels was working on some years ago. It basically uses a very sensitive cantilever or a compliant something that bends when you apply a force in order to measure the dynamics of magnetic moments. So in the classical way of conventional NMR, you couple these magnetic moments to an inductive coil, and you have some kind of a resonant circuit, and you measure currents or voltages in this circuit to measure the dynamics of this magnetic moment. And that turns out to work very well, although the signal to noise goes something like the volume of your coil that's filled with the magnetic moment. So the fraction, the filling fraction. And this turns out, to be very hard to make really, really small nanometer scale coils. And so trying to address nanometer scale samples becomes very difficult using that technique. And sort of recent progress in micromechanics, nanomechanics, atomic force microscopy has allowed us to make extremely tiny and extremely high quality factor mechanical cantilevers that make this kind of approach, where you have a cantilever with a magnet near a small magnetic moment, a much more sensitive way to measure the dynamics of this magnetic moment. So the basic idea is we just take a lever with a magnet and put it near our sample of interest to measure the spin dynamics. And this was first realized, let's say, with a modern AFM cantilever in the Rugar lab at IBM. And this is just these are some view graphs from the first paper in Nature in 1992. And it progressed quite a bit over the past 20 years, with a big milestone in 2004, where the IBM group was able to detect, using this MRFM method, a single electron spin inside of a dangling bond in silicon oxide. And you can see here the basic setup. You have some compliant cantilever, some magnet. You have your single spin over here. You address it with some NMR pulses, and you measure the deflection of the cantilever with an interferometer. Okay. So in the past few years, some version of this experiment, various versions of this have been tried, and the magnetic sensitivity has kept getting better and better and better beyond the single spin level, and trying to approach the sort of single proton level, which would give us single nuclear spin resolution. So we're not there yet, but that's sort of, we hope this trend will continue. Okay. All right. So. How does this technique work? Well, the fundamental tool that we use in this technique is our force detector, or our force transducer. And a force transducer is really quite a very simple object. It's, let's say, a cantilever, some kind of a diving board like this, on which you can apply some force, and it will deflect by some proportional displacement x. Okay, so if you want to measure small forces, you might imagine that you need some cantilevers that have very, very small spring constants, very, very small k, such that even very small forces will create large measurable displacements. And that's basically the first naive thing you would think about. Let's just get a cantilever with the lowest possible k. Okay, and if you just run through very simple Euler-Bernoulli equations, and you find out, how should I make my cantilever out of a given material in order to minimize k, you find that k goes with these geometric parameters. So the width, the thickness cubed over the length cubed. So it turns out you probably will want to make something that's really, really long and narrow, and that will give you the lowest spring constant. So that's quite intuitive. If you think about the problem a little bit harder, most of these experiments are actually measuring extremely tiny forces that are on the level of thermal fluctuations, even around thermal fluctuations of this cantilever, even when the cantilever is cooled down to like 1 or 2 degrees Kelvin. So in the end, the measurement technique is actually limited by the Brownian motion of the cantilever. So you have to measure forces which are larger than the random thermal fluctuations that this cantilever experiences. So what you should try to do is to make a cantilever which really has the smallest possible thermal fluctuations. And if you just write out what the thermal fluctuations are using the fluctuation dissipation theorem, you find that these thermal fluctuations have a spectral density given by this expression, where we have the temperature, the Boltzmann constant, the spring constant, some resonant frequency for the cantilever, and some mechanical quality factor for the cantilever. And what you can do is turn this spectral density into some sort of minimum measurable force. So you just multiply the spectral density by a bandwidth of your measurement and take the square root, and you find essentially that the minimum force that you can measure is given by this expression. So we should find cantilevers that really minimize this expression. And you can again go through Euler-Bernoulli and try to find out, well, which ones of these cantilevers, say, would be the best for this kind of measurement. So this is supposed to represent a sort of commercially available typical atomic force microscopy cantilever, which has a resonant frequency around 100 kilohertz and a spring constant of about 1 Newton per meter. And then these are some other sort of more exotic kinds of cantilevers that were tried, in particular at the IBM group in Dan Grugar's lab as potential levers for magnetic resonance force microscopy. And you can see there are some pretty exotic ones. This one is very, very long and thin and has an extremely small spring constant, but quite a small frequency. Some of these other ones have higher resonant frequencies and higher spring constants. But you can just sort of see which one of these might be best by doing some simple analysis of the thermal noise. So if we take this expression for the thermal fluctuations, we can just kind of simplify it out, and let's pull out some things which we're going to hold constant. So we pull out, let's say, the temperature, because we minimize the temperature to the lowest temperature that our, let's say, dilution refrigerator can achieve, or of about 1 Kelvin. And then we pull out the Q, because the mechanical quality factor, well, to be perfectly honest, we don't really understand how to control it. So let's just say we have it constant for any given material or geometry. And then we have these terms, which we have a little bit more idea how to control from simple Euler-Bernoulli theory. So we can write these out in terms of the geometric dimensions of the cantilever and some material parameters like the Young's modulus and the density, and you quickly see that this term is proportional to this expression. So the width, the thickness squared divided by the length. So again, the whole thing is proportional to this, holding these terms constants. And again, we find the same thing that we found before, that we should try to make cantilevers which are really long and thin in order to minimize this force noise. And that's why it turns out that this cantilever ends up having the best resolution for all of these, although these other ones should get close as well. Okay, and so that's why it's no accident that this kind of a single crystal silicon lever was used in most of the experiments that I'll be talking about. So this is a cantilever that's about 100 microns long. It's 100 nanometers thick, so it's extremely thin and very, very soft. And so it ends up having a very good thermal force noise limit of about 1 attonewton per root hertz, around 1 Kelvin. And there are sort of very similar kinds of oscillators which have never been used for doing magnetic resonance, but have similar force sensitivities. And this is just one recent example from Conrad Lehnard's group in Colorado at Gila, where it's essentially just a string made out of aluminum. So taking to this limit this very, very long and thin resonator. And they can also achieve this kind of record low 1 attonewton per root hertz measurement sensitivity. This might give you some ideas about what are the cantilevers of the future. There's been a lot of recent work in measuring, mechanically measuring things like nanotubes and nanowires. And just taking from a recent publication, I think it was in Science. I'm not sure if it was Science or Nature, but there was a paper from the Delft group on clean nanotubes where they were measuring some nanotubes across some bridges. And they measured some properties of these nanotubes, like the quality factor, the mass, and the resonant frequency. And if you plug these into our thermal noise expression, you would find that this is by 100 times the best force sensor that we've ever seen. So the problem that still exists here is nobody has quite figured out how to measure the thermal noise of these objects. But if you can do that, I would submit to you that the future of force sensing will be in these kinds of bottom-up grown structures like nanotubes or nanowires. Okay, so I talked a little bit about the cantilever. I'm going to talk a little bit about measuring small spin ensembles. This is obviously an important topic if we're going to measure nanometer scale volumes using MRI. So that's why I put up this graph. When you do a normal NMR measurement, you usually measure Boltzmann polarization, unless you've done some dynamic nuclear polarization. And what I'm plotting here is spin polarization in the sense of net spin polarization. So the difference between the numbers of spin up and spin down in a say a spin 1/2 system, as a function of the total number of spins in your ensemble. And if you then say you have a Boltzmann polarization, you see that this spin polarization goes down linearly as your ensemble gets smaller and smaller. Okay, so you can see when you start to get to sort of nanometer scale volumes, so these are sort of volumes of this equivalent number of of hydrogen spins for the density of normal materials, you'll see that you very quickly get to regions where you have almost zero spin polarization. So it will be very, very difficult to measure these kinds of volumes using MRI, using just typical Boltzmann polarization. And this, mind you, is not at room temperature. This is Boltzmann polarization at 4 Kelvin and 3 Tesla, so pretty say, but achievable fields. So what we've been doing in recent experiments is, instead of using Boltzmann polarization as a measurement of spin density, we've been using statistical polarization or spin noise. So this is just the fluctuations in the mean polarization that you have because you have some small number n of spins. So if you have an ensemble of n spins, they will have some variance around the mean of their polarization, which goes something like root n. Okay, and it turns out that for some crossover volume here, this noise is actually larger than the mean, and so becomes a much better signal to use as your imaging signal than the Boltzmann polarization. So in the experiments that I'll be talking about, we're always going to be in this regime where we have to measure the, let's say, noise rather than the mean for the signal. Okay, so this is actually something that was realized quite a long time ago in the 40s by Bloch, and in one of his seminal papers, there's a passage here where he says that, even in the absence of a magnetic field, there will be some magnetic moment of the order square root of n due to statistically incomplete cancellation, and that it's exactly this spin noise. And he goes on later in the paper to say, look, you don't have to worry about this, it's really tiny, it's no big deal, but in fact we're now getting to such small ensembles of spins where this is really something that dominates. Okay. All right, so I talked about a little bit the physics of spin ensembles. I talked about cantilevers. I won't really talk about strong magnets other than to say that we go to great efforts to make strong magnets. What I will talk about now is how do we actually realize this magnetic resonance force microscopy. I'll walk through the measurement a little bit and tell you about some recent results that we've had. Okay, so the actual cartoon looks quite similar to the figure in John's original paper. We have some cantilever which bends when you push it. We measure the bending using a laser interferometer. We have some magnet. In this case, you've seen we've put the magnet away from the cantilever, and we have some sample. In this case, I've drawn it optimistically as a single nuclear spin on the end of the cantilever. So we've inverted the position of the magnet and the lever, but because of Newton's laws, we're free to do this, and we can still measure the forces between them. What we will do here is, let's see. Okay, we will get a force between the spin and this magnetic tip, which goes proportional to the magnetic moment and the gradient in the direction of the cantilever motion, so the magnetic field gradient. And these forces tend to be really small, so if you calculate this for a single proton spin, you get some depressing number like 10 to the minus 20 newtons. And these are basically forces that are smaller than everything in the problem, including van der Waals forces at the distances that we work at of about 100 nanometers, electrostatic forces. These forces are basically only bigger than gravity. So you can see this is going to be a difficult measurement. But what I neglected to tell you is that we can take advantage of the magic of magnetic resonance to bring these kinds of forces out of the background noise. So this kind of red blob that I'm showing you is actually a microwire, what we call a microwire, essentially an RF short. We pass some RF currents through here, and that creates some perpendicularly time-varying magnetic fields in this direction. And using this RF short and sending some pulse sequences through here, we can essentially flip these nuclear spins at more or less any frequency we like. And what happens is we start flipping these spins at the cantilever resonance frequency. This causes a force between the magnetic tip and the spins to oscillate at the cantilever resonance frequency, and then this drives the cantilever into motion. And we read that using our interferometer. And this way we can distinguish the forces of interest from all these other forces which are sort of incoherently moving around. Okay, the other part about this that's interesting and that allows this to be an imaging technique is that, as John Seidels mentioned, we have very, very strong gradients near these magnetic tips. So at about 100 nanometers away from this tip, you can experience gradients of 10 to the 6 Tesla per meter. And that means that the field here is highly spatially inhomogeneous. And that means that if you have a particular resonance frequency in your pulse sequence, you will only address a very particular region in space. And that means your spins have to be inside what we call the resonance slice in order to be addressed by this protocol. And using this fact, you can actually scan your cantilever around and make images of your sample. Okay, so this is just a cute movie to sort of give you an idea of how this roughly works. We're going to apply some adiabatic rapid passages, so we're going to sweep our frequency through resonance, and every time this frequency sweeps through resonance, the spin that we have here flips, and every time the spin flips, this causes the force between the spin and the magnet to change sign, and then this slowly causes the cantilever to be driven. Now, of course, here I've exaggerated a lot of the scales, so please don't think that this is actually what the experiment looks like. But this is the basic physics behind it. Okay, and this is just sort of pictorially to show you how does this RF frequency protocol work. We make some RF sweeps through resonance. Every time we sweep through resonance, the spin flips. So in a perfect world, we'd get this oscillating spin signal. Of course, what happens is we don't live in a perfect world. There will be some random spin flips characterized by some spin correlation time. And so we'll measure signals that look more like this from each of the spins. And furthermore, we usually are measuring many more than a single spin. So if you add up 100 of these, 1,000 of these together in a very simple simulation, you get some signal which looks like this. And what you can see is it looks like noise at the cantilever resonance frequency. And that's right. And that's exactly what we would expect. The noise has some characteristic correlation time, which is given by the spins that we're looking at. And it has some characteristic amplitude, which is given by the square root of the spin ensemble. Okay, so if we then couple this force to our cantilever and read out the amplitude of our cantilever as a function of time, we should get some signal in the cantilever amplitude that looks like this sort of slow noise here. So this is all a simulation, but in fact you can do an experiment, and this is an experiment of about 1 million spins in calcium fluoride. And if you measure the cantilever amplitude with the pulse sequence tuned on resonance, you start to see some signal that most physicists would call noise, but I call signal, and with a correlation time of about 3.5 seconds and some large amplitude that corresponds to the number of spins. And as soon as you just go slightly off resonance, all of a sudden you get a different kind of noise, which is just due to the cantilever thermal noise, and you can see is very, very different both in its time dynamics and its amplitude from the spin signal. So essentially we measure this in order to see whether we have spins or not. And you can see here the time scale is in seconds here. You can look at this also in frequency space. You can just do a Fourier transform and plot the spectral density, and you can see that this cantilever thermal noise with the very fast correlation times is shown by this kind of broad peak here, and then this narrow peak that sits on top is the spin noise that I showed you with very long correlation times, and the area underneath this peak is the number of spins that you are in your detection volume. So when we do our measurement, we essentially take a lock-in and we integrate under this curve and plot this point, and we get some signal that is proportional to the number of spins. Okay, so this is an SEM of the cantilevers that are actually used in these kinds of experiments. So this is a big silicon wafer, big silicon chip, and we have our pure silicon cantilever. If you look at it more closely, it looks something like that. Okay, and the force noise in our experiments, the ones that I'm going to show you from our lab, at around 1 Kelvin are about 4 attonewtons per root hertz. So a little bit above, let's say, the record that has been achieved. And this is just to give you an idea of, we use the first fundamental mechanical mode to do our measurements, and this is the profile of the first mode. And this is what it oscillates, not very exciting. Of course, the cantilever has higher modes, and this is just the second mode, just to give you an idea of what it looks like. We designed the cantilever with this very large mass on the end in order to try to suppress this and even more higher order modes. And I can tell you a little bit why we do that, but essentially we can treat the object as only oscillating in this first mode that I showed. Okay, this is a picture of the actual microwire RF source and little magnetic tip, which is actually made out of iron cobalt. These are some samples that were realized in our lab in Basel. And with such microwires and tips, when we bring our cantilever with a sample very, very close maybe a few hundred nanometers from the top of that tip, we can get very large rotating fields at a few hundred megahertz, and we can get very, very large spatial field gradients of around 10 to the 6 Tesla per meter. So these are really critical parameters in order for this magnetic resonance force microscopy to have a high resolution. And these all have to be achieved in vacuum and at very, very low temperature. So the thermal heating due to this wire has to be minimized. Okay, so I guess I have 5 more minutes to talk a little bit about what's been going on in our own lab. So we've now built a system like this, very similar to what we had at IBM, and we've started doing some tests. This is just a picture of one of our first work in this, where we were testing some new geometries for this magnetic resonance force microscopy, where we've been applying the field in a slightly different direction in order to minimize magnetic dissipation. I don't really want to go into this here, but if you're interested, there's a short APL about this. And this is a picture of our system in Basel. So we have essentially our microwire chip with the magnetic tip down here. And then we have our cantilever chip here, so the cantilever hangs in this pendulum geometry. We have some positioners in order to move all of this, and we have a lens here, which is part of the interferometer to detect the cantilever motion. And all of this is at the bottom of a helium-3 refrigerator in vacuum. So what we've been focusing on in our lab in Basel is to, as I said, apply this to semiconductors, nanostructures, in particular 3-5 systems like gallium arsenide. And one of the things I'm really interested, because my background is in spintronics and in semiconductors, is to look at the nuclear spin dynamics in single quantum dots. And actually, quantum dots are kind of an ideal sample because they contain sort of 10 to the 4 to 10 to the 6 nuclear spins typically. And these nuclear spins are highly coupled to the electrons that are trapped in these dots. And it looks like MRFM, or force-detected MRI, is the only method that has a hope of directly measuring the dynamics of such small spin ensembles. So these people are interested in these nuclear spins because of their strong hyperfine interactions with the electron spins, and the fact that they are the major cause of decoherence for these electron spins, which are part of many proposals for quantum bits. Okay, so in our first efforts to do this, what we've been trying to do is to see if we can stick semiconductor nanostructures and heterostructures on the end of our cantilever in a similar way to the viruses that were on the end of our cantilever at IBM. So the ideal would be is if we could have our cantilever that I show here, and then we could cut out a little piece of a gallium arsenide wafer, maybe containing some quantum dots in here, or a quantum well, and to attach it on the end. Okay, and because what we really want is we want the interesting part of the sample, let's say the quantum dots or the quantum wells, to be as far out of the tip, as far out from the cantilever as possible, or as close to the magnetic tip as possible. So this looks a little bit like science fiction, and the piece that we would want to put on there would look something like this. Let's say we cut it out of a gallium arsenide substrate, and we have in here, let's say, some layer of quantum dots. And we want this thing to be really sticking out right here at the end of the cantilever. So we've actually tried to do this with one of my students using a focused ion beam in Karlsruhe, just to show that this can work. What he's done is he's gone to the focused ion beam, and he's used a focused ion beam technique, which is usually used in semiconductor failure analysis, and he's essentially used this focused ion beam to cut a very thin slice of a wafer out. Now, this wafer contains actually a quantum well about 100 nanometers below the surface, and what he does is he digs a trench in this wafer on both sides of the wafer, and he makes a little lamella, and then he cuts out the side from the top, and then he comes with a little a metallic probe, and he goes down to the little piece that he's cut out. He welds that probe to the piece with a platinum welding technique, which involves putting platinum gas into the focused ion beam chamber. And then he pulls this thing out of the wafer. And now we've got this little lamella with a little quantum well right beneath the surface here. He takes this, he brings it near a cantilever, which is also in the system, and attaches that piece to the end of the cantilever, welds it on with some platinum, and then you've got this little quantum well, which presumably is here, sticking out on the end of our tip. And in the end, what we have is our original cantilever, and now we've got this piece of gallium arsenide. It's mostly gallium arsenide here, and then there's a indium gallium arsenide quantum well in this case for this particular sample, but it could be any other heterostructure. It could be a layer of quantum dots. The main idea is here we wanted to see that we could do this and still have a nice lever. And the lever is, if you treat it the right way, will still have a nice quality factor and still work well as a force detector. So our first experiments, which we just recently finished on this, were essentially to put this in our MRFM system and just see, can we look at the gallium and the arsenic spins in this system, just the ones that are contained in this particle. Now, mind you, this particle is quite small. It has a volume of about 0.6 microns cubed, so it's a really, really very small volume to measure. And what we can do is do some basic force-detected magnetic resonance, and we see various signals. And you can see, we see a huge hydrogen signal. Of course, hydrogen has a very big magnetic moment, and hydrogen is everywhere. Any sample that's been exposed to air will have some contamination layer of hydrogen. So this is actually the large signal coming from just a few monolayers of hydrocarbons on the surface of the sample. And you can see this signal is much, much bigger than the signal from the gallium and the arsenic, although these are also visible. And the main reason is that the spin, the magnetization of these is about 4 times smaller, and because we measure things that go like the magnetization squared, then the signals are about 16 or 20 times smaller than the hydrogen. But nevertheless, we can get some signals, and if you calculate, well, let's see. Yeah, so we can get some signals, and a little bit later I'll tell you, how many spins these kinds of signals are coming from. So as I said, we measure statistical polarization for these spins, and the statistical polarization is slightly more complicated in a spin 3/2 system like gallium or arsenic. It's not a spin 1/2 system, so you just have to do a little calculation to figure out, what is the mean Boltzmann polarization of a spin 3/2 system, and what is the variance, sort of the statistical polarization, and that's given by this expression here. You can see it also, the square root of this will also go like the square root of n, although there's some factor that depends on the fact that it's a spin 3/2 system. And using these two expressions, you can see how small does the volume have to be for you to be in the statistical limit, where the statistical polarization is the most important polarization. So you can do a simple inequality. You can define some Boltzmann polarization from the expressions I gave before. So you can define some statistical polarization, and you can ask yourself, when is this important? When is statistical polarization larger than Boltzmann polarization? And you get some critical number. So below this critical number of spins, Boltzmann polarization is no longer a large signal. Statistical polarization is larger. And you can also equivalently, just using the density, turn this into a critical volume. You can see that it basically goes like the Boltzmann factor here, and it has some term that depends on the spin number of your sample. So it is a little bit different depending on the type of spin that you're looking at. So if we just look at the spins that are contained in or on our sample, you can immediately see what this critical number is. It's on the order of 10 to the 6 or 10 to the 5 nuclear spins, which you can, through the density, turn into a critical volume, which means you have to use a statistical polarization if you want to look at spin systems, if you want to look at volumes smaller than about 100 or 50 nanometers cubed. Okay. You can also define different receptivities in terms of MRFM receptivity versus the conventional inductive receptivity. I won't go into the details about that, but you can basically find that the receptivity for MRFM is actually scaling much better with the spin number than with conventional NMR. So actually, we're not doing. You have some better chance of measuring these high I spins than you do in a normal NMR measurement. Okay, and to sort of characterize the curves that I showed you before, we can ask ourselves, how many spins were we detecting on the peak of those resonances, and what is our spin sensitivity in all of those measurements? And you can see in all of the measurements we were around 10 to the 6 or 10 to the 7 spins contained in our signal, and we were sensitive to volumes below 50 nanometers cubed. So I'm getting signal that I should wrap up. I should just say that we have some plans to work on these, on doing some more interesting sample imaging, namely imaging nanowires and other kinds of semiconductor nanostructures. And this is just a picture of one of our latest efforts in putting a single nanowire on the end of the lever in order to map its gallium and arsenic density. Okay, so with that, I think I'll skip all of this other stuff and thank the students who did all this work and the funding agencies for the support.
A question regarding the cantilever damping. I was intrigued by your remark, kind of offhand, that we don't really understand where that Q comes from. And so it seems to me that's a really fundamental question for not being in this field. Maybe I got it wrong, but.
Yeah, no, it's an excellent question. So, I mean, there are, in the sense, I say I don't really understand. We understand that there are many reasons why we should have dissipation, in other words, a decrease in Q. There are lots of different means by which you can lose the energy in the course of oscillation, which is essentially dissipation. And the question is, what is the one that's limiting us? And typically for these kinds of structures, the ones that you worry about most are clamping losses, so losses that have to do with how the cantilever is attached to, say, this big large chip or the substrate. And other kinds of losses have to do with surface states and the quality of the surface and whether there are metastatic states which keep sort of switching around and dissipating away energy. There are other more subtle effects. If you put these cantilevers in a magnetic field and they have any kinds of magnetic objects in them, impurities or so, this can lead to dissipation. We observe this sometimes when our cantilevers are not particularly clean. Even though they should be pure silicon, we observe magnetic dissipation, presumably from magnetic impurities that are introduced in the processing. And because these things are sensitive to such small forces, you can see very, very, very small effects. But the reason I sort of left it out is because there have been many efforts in MEMS to reduce these kinds of effects, and I would say that there isn't a coherent theory as to what you should do to minimize Q. My own intuition is you should, and one of the reasons that you saw we never have these magnetic particles on our cantilevers and that our cantilevers look relatively simple is that you should try to take the purest possible material and do the least amount of processing to it in order to have the best Q. And don't attach anything foreign that's very large to it. And also make sure that your surfaces are as smooth as possible or as crystalline as possible. Now, I think this is also one of the reasons I'm really intrigued by going into nanoresonators that are really, let's say, made bottom-up, that are self-assembled, that are like single crystal, like a nanowire or like a nanotube. These, in principle, should have the best Qs you can get.
That leads to the question, why don't you just make the cantilever out of gallium arsenide?
Yes, that's an excellent question. So part of it is practical. We've been working with these silicon levers for a long time, and we've really optimized how to handle them. Gallium arsenide is a good material for these kinds of systems. It would be very interested. I'm interested in making these levers. It's just a little bit more technologically difficult to process in terms of making three-dimensional suspended structures. So it's more brittle. It's more fragile. It doesn't survive certain processing techniques as well. Also, there's a lot of strain in some of those systems, and this can cause cantilevers to like curl back or not to be completely straight. So I think we're a little bit a victim of the fact that silicon processing is really, really advanced, and gallium arsenide processing is not quite at that level yet. But yes.
Point perhaps, are the spins in the cantilever itself reflectable there?
So the silicon spins, as far as I know, we should have to
29, for example.
Yeah, we should have to worry about silicon 29. Actually, we've never tried to look at these. In principle, we may have the resolution to look at that, although I think it's less than 1% or so is the natural abundance, and so probably the signals would be quite small, given the fact that the magnetic moment is also small. But in principle, we could measure these too.
Okay, but that was probably when you try to scale down your sample. Perhaps. When you want to reduce your number of spins to investigate.
Then
it will perhaps be more problematic.
Yeah, sure. Yeah.
Can you say simply why you don't use one of the harmonics of the cantilever? Because at first sight it would appear that might give better results.
Right. So some of these, you basically have to calculate a different spring constant for most of these harmonics.
Right.
And because they displace a little bit less, then they end up having usually stiffer spring constants than the first one. And so this ends up giving you not so good force sensitivity. Although I think the real reason that we don't use it is that we try to think in the simplest way possible we try to simplify each component of a very complex experiment. And so using the fundamental, where it's quite easy to sort of linearize the motion into the motion of a simple harmonic oscillator, is much easier than going to more complex modes.
Okay. The other thing, you've just not talked about the laser at all.
Yes.
Now, this is probably off the wall, but of course the laser imposes a force on it as well.
That's right.
And that force has got noise.
Yes.
Is it totally negligible?
So it's not. So actually, it's an excellent question. And I just came from a conference on opto-nanomechanics, where this is essentially the entire field, which is the interaction of nanomechanical objects with photons. And there's a radiation pressure force, and indeed, this radiation pressure force does affect our measurements for certain powers. We try to stay at very low powers. We use 1550 nanometer light, so very low energy. We use about 20 nanowatts of it incident on the cantilever, and we have a very we use an interferometer cavity that's very, very low finesse, so that the laser light doesn't stay inside the cavity very long, and so these radiation pressure forces during our measurements are negligible. But you don't have to turn the laser up very much to see these effects. And what you end up,
trade-off then.
it's a trade-off. And what you see is, depending on which side of the fringe you are, you can either see heating or cooling of the thermal motion due to exchange with the photons. So essentially, photons become phonons, or phonons become photons. And there's a whole field dedicated to this, to using this for cooling cantilevers to their ground state and so on. And we have done a little bit of that, but we haven't really seen any advantage in terms of using these techniques to get higher force sensitivity. Because if you work through it in the end, you always end up getting the same force sensitivity.
Okay. Nice.
All right. I think the most pressing questions have been asked. Thank you very much again.